Hi everyone, welcome to this year's Doors Clock conference at FAIR, the first day. And for our first lecture, we have, Davor and Goran, who will be telling us about the ULX3S fully open source FPGA development board with fully open source hardware and which supports a fully open source toolchain. Yeah. So without further ado, I'm gonna give the microphone to Goran. Excuse me. So let's give it to Goran.
Hi to all. I am Goran and I am from the makerspace Radiona, and Davor is the author of the ULX3S board. So he will talk more about it. I'm in the project. I'm mostly promoting it and doing some prototyping and soldering and some experiments. So Davor, you can.
Okay. Okay, hello. I would like to present this board, which we were working several years. It is a result of the collaboration between the Makerspace Radiona, Faculty of Electrical Engineering in Zagreb, Konjar Industrial Electronics Department, and some kind of hacking, because we would like to, we wanted to design some board which could be used on the several applications. This is the FPGA board, which in basic replaces some of the hardware problems into the software domain. So before, you probably would like to assemble a complex board from the individual chips and wires and solder it together and make a CPU or some other hardware digital device. And now FPGA makes you do it without hardwaring and soldering, just by telling the chip in some language, which is hardware design language, either Verilog or VHDL, to make such a device using a universal board. This is my first board, which I obtained from the faculty of in the shop. It's used by the students, but it's also it was also a very beautiful board for the experimenting. It is used since last year for the lectures, but after the years passed, there is some kind of development in the market, and the available chips are much better, much more capable, and this board is of course missing few of the features like video, more buttons, more something. So after this board was successfully used, we wanted to have a list of the new features which we would like to have in our new, let's say, product, which I wanted to have for my personal experimentation and work and everything. I couldn't buy it, so this is the main motivation why I want to design something, because there's no such product on the market. I want to have it and make it, and if I want to have it cheap later to buy it, I must pursue some kind of organizations to also accept it. So I was asking the faculty and Mr. Marco, who is happily here, what do you need for the students? And he said, I need the buttons, I need the LEDs, I need USB, and this is what I need, and must be cheap. Not much expensive from the parts like old board. And then I added additional list of the features which you see, which includes wireless, which includes HDMI, which we called differently because of the which we cannot obtain a certificate, so we called GPDI, General Purpose Differential Interface, which has compatible pinout and the connector. You can plug the monitor on projector, and you will see the picture. So all this presentation is run on the board, actual hardware, which I hold in my hand. I have no laptop here, and on each press, the software inside will make it. So we will have SD card, we have additional buttons, more audio channels, video, as I say. We have display, placeholder for onboard OLED display, so this can be a standalone device. New features is also RTC clock. So this board can go to the low power sleep, about 10 milliamps, and it can be wake on any time using the RTC clock. This is rarely seen on the market, so I'm not sure if you can get it officially. Maybe recently, but when we designed, not so easily. Let's see. 1 year or maybe 1 year and a half, I needed to design the board. It was a number of releases, I don't know, hundreds and thousands of revisions. Everything is on the GitHub. So we initially started from the design of the PCB. It must be maximum 10 times 5 centimeters. So let's place anything which fits on this size on the board. When we use all the space, we are done. So it took us, of course, some time. On this board, also, which is not often seen, is this purple line is the antenna. So this board has hidden antenna, which can use as a remote device 433 megahertz, or you can do FM, I don't know, like RDS, you can play sounds or so on normal radio. This is a product completely done. All the important features are on the upper side of the board. So it has also some visual appeal. If you want to buy it, it's nice as a complete board. It looks fine and organized, cool. You see the buttons on the right side. There is a memory chip. This is SDRAM. We chose an SDRAM because of most of the open source project supports SDRAM as the RAM controller. So for example, if you need some retro computer emulation, if you have SDRAM, you will have no problems. If you have DDR, you will have some problems because DDR has some latency, and some of the retro hardware can't be done on the DDR. It can be done only on the SDRAM, and we have it. Central chip, of course, is FPGA, which can have a range from 20 to 85,000 logical elements called LUTs. On the left side, you see SD card slot, and on the back side, this is Wi-Fi. This is Wi-Fi chip, ESP32. This board can have how can I say, web interface, so you can either program it, control it, upload it, maintain it. It has USB clock, USB, and let's say on the back side is power section. We have done very much care about how stability from the power side can this board do. So this board must be supposed to handle short circuits. It must power external circuits. It will have 2.5 and 3.3 selectable voltage on one controller and 3.3 volt on the other controller. More than 1 amperes is available for the power supply. Also, the external connectors are PMOD compatible, so you can solder some PMOD and plug it, and it will work. From detailed view, this is the FPGA chip, this is the RAM, this is the flash. Usually we ship it with a 16 megabyte or when we do it as a Radeona. You can also have cheaper variants for the students. It has 4 megabytes, it's also okay for everything what you need. This is what I mentioned, SD goes here, 8 LEDs in the cascade, so you can display a byte and it will be seen as a bits in the binary form. This is the buttons, it works, and this is usually used for the lab exercises and the students. Fix deep switches. It can serve the same as buttons, but it remembers its position. This is GPDI, video and monitor digital goes to there. New audio. This audio has 3 DACs. DACs can be used for normal left and right stereo, so you can plug earphones and you can have a nice sound from this. It will be loud and audible. But it has also the third channel on the additional ring. On the additional channel, you can either display old-time video like composite, or you can use as SPD digital audio. So it is new on this board compared to other. Also, this is new on this board, the ADC chip. Can be from 8 bits to 20 bits, depends on the price. So cheaper models are sold like 8-bit chip. That's ADC, and new ones 20-bit. 1 mega sample per second. It's not too bad, and it can also do differential. I forgot to mention that most of the connectors on the external are also differential. We have 20 differential pairs, true differential, and so you can use ADC either in differential mode, and also you can use FPGA on differential mode. And normal on single-ended digital, like everything. This is the our Wi-Fi chip, ESP32, completely integrated, so it can done remote JTAG, it can reprogram the board, reflash it, it can take control the board, and also it can use as a board's external interface to the Ethernet, to the, I don't know, TCP or web interface, whatever. Normally ESP32. This is the battery and RTC controller. So this one is responsible for waking up the boards and taking the clock. It ticks if you have the battery. This is the mentioned power section. We have 3 of such power section, copy-pasted. For the 3 required voltages of the FPGA, it needs 1.1, 2.5, and 3.3. And the last 2 are also externally available. 1.1 is also only internally available, connected to the FPGA, but usually you can connect some wires if you really need some voltage, you can get it outside. Primary USB connector is used together with chip FTDI 231X chip. This chip can do USB JTAG a little bit hacky way, but it works. We have several possibilities to program it. I will show it later. But from Linux, Windows, and Apple, there is some solution. Usually with some tweaking or hacking, you will get it compiled and work, or we also ship some binaries, of course. This is the external JTAG. If everything fails due to the programming, solder 6 pins and use your reliable JTAG, whatever it is. It can be and work directly as a hardware. Upwards is OLED connector, 7 pins. You can buy from eBay for $7 small OLED, which has true color display, 96 times 64 pixels, and it's nice. So these are 3 programming or 4 programming options. So we can program it using USB. And we have some open source programmers. UIProg, FliFPGA, JTAG, and OpenOCD work for Linux, Windows, and Apple platforms, more or less. Who has problems, let us mail. JTAG can go directly, as I said. ESP32 can also take control over the JTAG using the web interface and so on. The 4th option is also the second USB port. This port can take a bootloader. This bootloader can be compatible like tiny FPGA, but we also have some forked modification, which I think is more reliable. I was doing it. But it's not absolutely reliable, so if you need reliability, it's best to use external, but 99% of the people can handle other 4 options. I think you won't be left away out of the options. One of the options will program your board. This is for sure. Web interface looks like this. So you can choose any file. You can place this file on the SD card if it is on board, or you can directly send SVF file into the FPGA. For example, if you place this board on the remote, if you have it on the high voltage unit or something which you can't touch or don't want to go directly to the board, you have options to remotely control and reprogram it, reflash it and everything. Sometime it will break, of course, but you know. Other options, you can do some retro gaming. We have a lot of possibilities. This is Phoenix. I will show it how it runs later. This is Amiga emulation. This board can do it also. I will demonstrate it. This is Oro computer, some kind of old computers from Yugoslavia. This board can also emulate. This is Galaxia, also from Yugoslavia board, also emulated. This is what Goran did, a small LED display from the panels. It can be really big. This board can drive it. If you want to hack it, replace the RAM with some bigger chip. This is 64 megabyte. And we have also our core F32C, which was done on Faculty of Electrical Engineering. Marko Zec was mostly doing it. I'm maintaining currently some kind of external drivers for this. This is MIPS RISCV compatible softcore CPU, which is not only for our boards, it runs for Altera, Xilinx and everything, but also our board has fair support for it. This is a listed number of the features. You can do it. This is example which this softcore runs online on this board. So it's a sprite engine, 2D acceleration, which you see it on the runtime. It really runs on this exact hardware which I'm holding on my hand. I can, by the button, switch it and it will work. It's so fast. So it's about 200 sprites running in sync with the vertical blank, and it runs smooth. We have also in the softcore vector processor, it's a FPGA acceleration unit, which in the simple words does something like this. If you have 248 floats, you can do in the for loop some basic operation plus minus division in 48 clocks approximately. If you, okay, maybe a few clocks extra, but it's order of this complexity. And this vector processor is fully featured, so it's not only something like that. It can do everything on even more than everything that had a Cray computer, if somebody have heard it. It is all-time computer from the 1770s, which is a supercomputer about 300 megaflops. I guess it had 280 or something. So this board has approximately the same capacity which this supercomputer had it in 70s, also in the vector unit. Yes, this is the Fractal this vector unit has calculated, so it is quite fast. Okay, it's not so fast, it's not so this one, it takes several seconds to calculate it, but okay, it is really fast. If you calculate it on normal processor of this type, 100 megahertz MIPS, I don't know, even with normal floating point unit, it will take minutes, tenths or 5 minutes or something like this, not 6 seconds. It's nice. So you can have many other experimentation in the Verilog or VHDL. So this is open source stuff. You can add your own hardware. You can make some kind of memory map unit. You can take, for example, this is a GPIO part of snapshot when it reads and writes registers. You can copy GPIO, start it from this, and make your own additional hardware to this processor. Take it for our board and try it. If you have problems, ask me. I'm sure if somebody experiments, sooner or later he will find obstacles. But it works for us at 100 megahertz on this board. Also, we have Arduino interface. So in the Arduino, you can have blinklets, and as well, this complete presentation is Arduino Sketch, which runs in real time. So this is a snapshot in the Arduino. When I press a button, how it changes the pictures. Every picture is a sprite from the hardware acceleration unit, and on the press of the button, a new sprite is shown and other is hidden. So you are looking at the sprites on the on the display. This is our website on the GitHub, which you can download binaries. Take normal Arduino, get our binary, and make some installation. So I will, in the short, show you how it's done on our Arduino. Yes. Okay. Yes. This is somebody who wants to go. This. You must click that, and this, and your board will work. I will now try to also show you Amiga, if it works. I guess it works. So we are running on the time. Let's go to the questions, and during the questions, I will also control the board. Any questions? Okay, as long as no questions, somebody will ask. I'm sure. Let me see. Amiga games. Yes. So now I'm on the emulation of the Amiga computer. You know, I switched the presentation to the Amiga, and this is some game of the Amiga. It's supposed to work. Let's see, does it? Yes, I can drive. I can shoot stuff. Yeah, it works. So this is Amiga. Yes. Oh, I forgot it. This FPGA is available as in a shop. 100 meters from this site is a Skriptarnica shop of the faculty in which we are now. Go to the Skriptarnica, about 400 kunas. This board can be normally obtained. You can have 20K gates for this size, and everything what you see on this presentation will run on your board, what you can get and start working. So yeah, right. Good idea.
And for the 85K boards, you need to contact the Radiona. So for the 85F, you need to contact Radiona. We are now in the process of making next 100 boards, so contact us.
Yes, right. So this is also some other retro games running on this board called Scramble. I'm showing you a multi-boot feature of this board done using the open source tools. So open source tools reverse completely this chip, which is AC, almost completely, let's say, this Lattice ACP5. And we know how to access usually hidden features from the manufacturer. On the same flash chip, I have placed several bitstreams, and on the press of the button, I'm triggering the multi-boot feature of the FPGA chip, and it will switch to the next bitstream stored in the flash. So one bitstream was the presentation, the other was Amiga, so it's Scramble, Phoenix, this is Froger, and so it goes as long as your flash has some size. About 1 megabyte, depending on the FPGA size, is the length of the bitstream. Let's say if you have 4 megabyte flash chip, approximately 4 bitstreams will fit. If you have 16 megabytes, then you have about 16 bitstreams on the smaller board, or maybe 8 bitstreams on the larger board, but these are some kind of possibilities. Yeah, so I'm glad that it works, and if you, I can say that this is the easy for starters and newcomers, because you are supposed to understand programming and the VHDL or Verilog language. These are programming languages. They look like ordinary C or something Python and in between, but logic behind of that is different because everything runs in parallel. So normal standard C or procedural language will execute each line one by line, and this lines which you have written go converted into the hardware in some kind of a silicon which runs basically parallel, and you must take care of the parallel issues which will be happening inside of the chip. This is different, and you need to switch your thinking when designing. But okay, good for refreshment. Is some more questions around? Yes.
I have two questions. First, is the Bitstream format open and documented?
Yes. Is the Bitstream open and documented? Yes, it is. I mean, or maybe it's not really open. I think Lattice tried to open it mostly, but David Shah from England, he is completely reversing everything, including this Bitstream. So we know Multiboot feature of the Bitstream, which was recently discovered, and standard boot of the Bitstream was long time known by the open source community. So yes, open source tools completely generate the Bitstream. Only feature which we don't know yet is the compression. How is compression really done? We don't have example in the open source. Lattice somehow supposedly released the format of the compression, but nobody yet implemented and proved that it really works. So in this documentation, as we know from the before, can be some bugs. Until it works for real, we can't say that compression. So because of this compression, your flash, if is done by the open source tools, will fit less bit streams. So if you had compression, you can go less than 1 megabyte per bit stream on the largest device. Without compression, you must count about 2 megabytes. Something less than 2 will be this bit stream. So this is the only limitation. Compression is missing. Everything else except compression is known by open source tools, and it is regularly done.
Okay, and another question. You said there's a board available with high capacity that you're preparing. How can we contact you, and what would be the approximate price for the largest one?
Yeah, for the largest one, we still don't know a price, but
Okay,
probably our bit around 120 euros. Yeah.
so let's say first repeat the question. So question was what's the price of the largest device and how to contact it?
Yeah, so we are doing the small quantities of the board, and then it's a problem with the production. So I think that the price for the 85K with the 64 megabytes of RAM and the ESP32 will be around 120 euros. So yeah, it's, and for the second question was where you can contact us. It's ulx3s.fpga@gmail.com. So then, or Radiona, yeah, it's, yeah, Radiona website has all information about and we have the site for the ULX3S, but if you put the ULX3S in the Google, you will find us. So it's that is not the problem. Yeah.
Okay. It's finished.